He is going to talk about storage. There's a big center, CEEESA at Argonne. He's actually not working at Argonne. He works from there's a little college there on the river. I don't know if you guys heard of it, called MIT, small college. That's where he's working right now. But he's still. He assured me he's still an Argonne employee. So I'm very happy that you're here to talk to us.
Right.
Thank you for coming.
Sure. Yeah, thank you so much. Do you hear me? Okay, good. So thank you very much for the invitation. What I'll be talking about is some of the work we do on renewables integration, and specifically about a new project related to energy storage. Yeah, it's nice to be back here. It's about 8 years since the first time I came to give a similar talk. So a few words.
Increase your frequency, okay?
Yes, that's right. So a few words about the place I work at, Argonne. It is one of the national labs under the Department of Energy. It's a fairly large research facility outside Chicago. You can see the numbers here, about 3,000 full-time employees and a broad range of research and development activities. And the main sponsor is the Department of Energy. And the group that I work in, the Center for Energy, Economic and Environmental Systems Analysis, we do work across a range of areas within power and energy systems. Some of them are listed here. From forecasting of renewables to optimization models for planning and operations of the power grid. And also, more recently, we are getting into things like cybersecurity, grid resilience, and also we have some large computers that we sometimes try to apply on power systems problems. Okay, so what I plan to do today is I have a few slides first, which shows some of the work that we have been doing on integration of renewables. And then the second part is more on energy storage. That's a relatively new project. So that's definitely work in progress, but I'll show you some preliminary result where we're looking at stochastic unit commitment with energy storage. And also a model where we try to optimize the energy storage bidding into day-ahead and real-time markets under uncertainty in prices from the storage owner's perspective. Okay, so and some of the motivation for this work, as you probably know, the U.S. power sector is a significant part of the economy, and perhaps more importantly, it's a large emitter of greenhouse gas emissions. And there has been and still is a rapid change towards more renewables. And the installed capacity in the US and worldwide of wind and solar are shown there. And these are starting to have some fundamental impacts on how we operate and plan the power grid. So one example here is from MISO. I guess we are in the MISO area now, right? Back at Argonne, we are in PJM, but here we are in MISO. So this is hourly wind power output a couple of years ago in MISO. So there is definitely variability over the course of a month here. For solar PV, this is just for one day, one specific site, the irradiance. For a sunny day, the red line. For a cloudy day, the green line, and then a day with intermittent clouds, which is the blue line, which is very hard to forecast, at least for a single individual site. So the key is to address these variability and uncertainty issues in power grid planning and operations. And also these things have impact on electricity markets. This slide shows prices at a node in MISO. The red line is from 2008, and the blue line is for 2012. And in between there was a large wind farm constructed right next to this node. So this is the LMP in the day-ahead market, and a couple of things you can see here is that the overall price level is much lower. That is probably mainly due to lower fuel prices, but you can see it starts to occur much more frequently that you get negative prices, and that of course gives you some weird incentives if you operate in the power grid. So this is just for one specific node, but if you start increasing the penetration of renewables across the board, you may see these types of developments other places as well. So one thing we've been working on is forecasting, improved statistical methods for forecasting. The argument is that in addition to forecast, to make a deterministic point forecast for how much wind power you will have for the next hours and the next day, it's important to estimate the uncertainty in the forecast. And we have been looking at one method which is called conditional kernel density estimation, where you establish a relationship based on historical forecasting errors to make a conditional, a forecast which is conditional upon certain explanatory variables. And one example is here that you can forecast, or if you forecast if you have wind speed on this axis and then power production on this axis, if you are in the middle range here, you have a wide probability density function. You have more uncertainty than what you have with lower and higher wind speeds, because that's where you are at the steep part of the power curve. So if you establish this relationship based on historical data, you can forecast the wind speed, and then you can derive a probability density function, which may look something like this for the amount of wind power that you'll get for a certain point in time in the future.
Let me ask you a question.
Yeah.
If the wind speed is 0, how could you get non-zero power?
So this is the reason is that this is forecasted wind speed.
Oh, that's forecast. Okay.
Yeah, right. So there is uncertainty, in this observation here.
So which is the vertical axis, one perpendicular to the plane?
You mean in the right-hand figure or in the left hand?
Yeah, to the right. What is that?
That's a probability density function. So we have forecasted wind power here from 0 to 1.
And that's just the wind power then?
That's a probability. It's a PDF basically. So the area under the curve is 1 here.
So on the left graph is the vertical axis, that's forecasted wind speed, and is the other axis actual wind power?
Yes, that is measured wind power. Okay. That's right.
So you're relating forecasted with measured.
Mm-hmm. Yes, and you can do this in multiple dimensions, but wind speed, of course, is the most important explanatory variable. So that's one piece of the puzzle that we've been working on.
Per unit is what? Based on the rated capacity of the
wind farm. Yeah. So we typically do this for one wind farm. So if you have a 200.
So is this a wind farm forecast? Is it like for say 100 machines?
Yes, something like that. That's right. But it's one location, Okay. I want to mention that we also have moved into solar power forecasting. This is a new project, or relatively new, which is led by IBM, and they are applying machine learning methods. You can see the name Watson, similar to the Jeopardy a couple of years ago. So the idea is to use machine learning and big data to come up with better solar power forecasts. And then there is an important intermediate step. You have to, I don't know if you see what I'm pointing at here, but you have to forecast the irradiance as an intermediate step, which you don't have in wind power forecasting. But then in our group, actually most of the work that we are doing deals with the power grid and how to make use of this information in operational and planning decisions. And one of the ideas that we have worked on, along with many others in recent years, is to look at stochastic unit commitment, where the idea is to, traditionally you do the unit commitment based as a deterministic problem. But you introduce uncertainty through forecasted scenarios, and you minimize the expected operating costs over a range of scenarios, subject to the regular constraints that you have in unit commitment and economic dispatch problems. And you can apply this at different stages of market operations here, from day ahead to what's called reliability commitment to real time. And we've been trying to compare the stochastic approach with dynamic reserves and simulated the system over time to see, which of those approaches that give you the lowest operating costs. And so far,
Are you representing there also the rampability requirements?
yes, there are ramp constraints.
Okay, I don't know which equation.
Well, it's actually, this is just a high-level description, but it will go into the unit commitment constraints. So you have ramp constraints on the generators, how fast they can ramp in an hour, and also in a matter of one minute. So we do consider the ramping needs. So I'm going fast here, but just ask questions, that's fine. So what we found in this study was that if you move from fixed reserves, which is kind of the standard, the traditional approach, you move into dynamic reserves, where you estimate the reserves based on the amount of forecasted uncertainty, and you could go all the way to stochastic unit commitment. You tend to be able to reduce your operating costs when you move from left to right here. So it seems like there is, based on this analysis from Illinois, that there is some value to using stochastic unit commitment. But if you compare to the dynamic reserves approach, it's not huge in this case. So, it's a question of whether you want to make a relatively big leap in terms of the types of tools and methods that you use for what may be a relatively modest benefit. Yeah. Right, so basically the difference is that when you go from left to right, you increase the amount of reserves that you build into the model. So yeah, that's right.
Adaptively?
Well, in this case, you do it adaptively with dynamic reserves. Then you look at the quantiles of your forecasted distribution, and you adjust the reserves accordingly. But we use a more stringent rule as we move from left to right here.
Yeah, but it depends on the quality of the forecast? Is that what you're saying?
It depends. So we have a forecast that looks like something like this here with forecast quantiles. So we look at how wide that distribution is. And based on that width, we determine the amount of reserves that we impose on top of the unit commitment problem.
So you're working on a 24-hour horizon, right?
Yeah, yes, that's right. That's right. And yes, we've been looking at some alternative formulations of the stochastic unit commitment problem as well. Traditionally, you do this in 2 stages: commitment first stage, dispatch second stage. This is work that we've done with Professor John Birch at the University of Chicago, where we have a more flexible representation of commitment decisions, and we basically show that you can reduce your operating costs by using a more flexible stochastic unit commitment the decision. I'll get back to that later in the talk, actually, with energy storage. Another aspect is that typically operating reserves are just fixed requirements, but from an economic and market perspective, the value of those reserves depends on how tight the overall supply-demand situation is in the market. So another idea that we've been working on is to derive demand curves for operating reserves, downward sloping demand curves, which also reflect the uncertainty in the wind power forecast. So like for this day here, where you have low load and high wind power uncertainty, so we convolve the uncertainty from thermal generators, from load forecast uncertainty and wind power forecast uncertainty. And you can see how the demand for reserves shifts from left to right with those contributions to uncertainty. And in this case, you can see that wind power has a large impact on the amount of reserves that you need. On this day, with high loads and low wind power uncertainty, you can see that it's mainly the thermal forced outages that drive the demand for operating reserves. But when you move to this downward sloping type of reserve, that has implications for market prices as well, because depending on how tight the situation is, you keep climbing up or down this curve, instead of having like a vertical demand curve, basically, which is the traditional approach.
I'm a little bit confused. Yeah. You call the blue line thermal plus load plus wind.
Yeah.
What is that?
It is basically, so we calculate the need for reserves is a function of three sources of uncertainty. The first one is thermal outages of thermal generators. The second one is load forecast uncertainty. And the third one is wind power forecast uncertainty. So we do these calculations adding one uncertainty at a time here. So that's what's shown here in these graphs.
But your axes are demand and prices.
Yes, demand for operating reserves.
Oh. That was the demand in terms of your load.
Oh, sorry, yeah, it should, yeah, demand for operating reserves. So this is all about operating reserves. But when you co-optimize this in the energy and reserves markets, this curve will also influence the energy prices.
So what is the difference between thermal and thermal plus load?
So thermal plus load, there you add load forecasting uncertainty on top of the forced outage rates of the thermal generators. So you convolve those uncertainties. And you combine that with a value of lost load estimate to derive these type of curves.
Yeah. So those are thermal units.
This
uncertainty, right?
Yes.
And the load is the load forecast uncertainty.
Yeah.
And the third part is the wind forecast uncertainty.
That's right. Yes.
Okay, so that's what we're looking at.
Yeah. Yeah. Question.
So I see a trend in that when you're accounting for the risk of load included, the price goes up, correct?
Yeah, basically you want to have more reserves.
But on this graph, how come with between like 0 and about 500, yeah, you see a drop there, shouldn't it be higher?
Yes, that's a good observation. I know we talked about this. That there is a good explanation. It has to do with the fact that load forecasting uncertainty can be both positive and negative. So that's basically why you see that. I think that's the explanation why you see that at the very low, you know, up here. Anyway, this has influence on prices and also, and therefore how much profits the different generators make in the reserve and energy markets. And this graph shows that with a demand curve approach, you have a much more stable revenue stream. If you compare that to the fixed reserve approach, where you have basically a vertical demand curve, then you get price spikes once in a while. But very often the price for reserve is zero. So you tend to get like a more stable price for reserves with this type of approach. And this is actually what they are relying on in ERCOT in Texas to solve the long-term capacity adequacy problem through a demand curve like this, instead of having capacity markets like they have in most other systems. Okay. We've been looking at emissions as well, and also solar PV integration, a study we did in Arizona. So just briefly, one of the things we did here was to look at the balancing performance measured in terms of CPS2 score, compared to the estimated cost of integrating solar PV in the system. And the NERC requirement is that you have to be above 90% CPS2. So it means that the utilities actually have quite a bit of flexibility if they like to decide on how tight they want to balance their system. But the integration cost changes accordingly. So, you know, if you have a low CPS2 score, your estimated integration cost is low, and vice versa. But traditionally, most utilities like to be up here in the 98, 99% CPS2 score. So that's one interesting observation. Another thing we've been looking into is longer-term expansion planning, and the fact that baseload plants, in particular nuclear, are very concerned about making a profit when you get more renewables that tend to drive down prices. So we have some modeling work where we look at optimal generation expansion in a longer-term perspective with different increasing levels of wind power. So here you go from 0 to 30% with 4 different assumptions, and you see what kind of power plants you tend to build from an optimal planning perspective for different wind penetration levels. And down here, for low penetrations, you build a little bit of baseload coal, but as you get more renewables, you switch to combined cycle and natural gas entirely. And a different, a related part of this story is that this impacts the prices and the revenues in the market. And the short story there is that if you are a baseload plant, it's likely that you're getting into trouble as you get more renewables in terms of covering your operating costs through market prices. If you are a flexible combined cycle or gas power plant, you are more likely to make a profit. Okay, so we are working on various operational planning and market design challenges in the context of renewables, and oftentimes we collaborate with other institutions like NREL in this case. This is a new report which is discussing market design challenges under increasing levels of renewables. And also we work with a number of universities. We oftentimes have students, summer interns helping us out at Argonne. Some of them are listed up here. 2 of them actually are UIUC students that we had a couple of years ago supporting our activities. Okay, papers and reports are available if you want to look at the details here. But let's move on to the energy storage challenge here, and how energy storage can be used when it comes to integration of renewables. This project is a relatively new one, so I should say that the results that I'm going to show you here, they are preliminary, and I like to point out Nan Lee from Arizona State University and Deepak from Iowa State. They have been working with us this summer, and they deserve they have done most of the modeling and simulation work that I'm going to show you. So they deserve praise for that. And then we are some people across different divisions at Argonne supporting this project. And for energy storage, you may have seen graphs or illustrations like this. This one compares the power ratings, how much power you can draw from the storage device, and the discharge time, from seconds up to hours. And up in the upper right corner is the pump storage hydro, which is currently the one large-scale storage technology which is frequently used. Compressed air is also up in that upper right corner with large capacities. Long discharge times, which means that you can store a lot of energy in those facilities. And then you tend to have batteries, somewhere in the middle here, and supercapacitors, of course. And down here you have, high power supercapacitors, which only can provide energy for a very short amount of time. The same is the case with flywheels. So it's a landscape of different technological solutions. And lots of people working on developing and improving technologies, hoping that they will be able to become, profitable solutions for the power grid. And there are comparisons out there on costs and performance of these different technologies. This one is from a couple of years old, comparing different batteries with pump storage hydro and compressed air energy storage in terms of lifetime, efficiency, and different ways of calculating capital costs. I guess the short...
Whose chart is this?
That's the International Renewable Energy Agency, I think. The short story is that, again, pump storage hydro is really the technology to beat here. It has the longest history, the longest lifetime, and tends to have the cheapest cost as well. And if you look at the amount of energy storage in...
Do you trust that figure?
This one?
In terms of, because I just don't think of pump storage as being very cheap.
Well, everything is relative. It depends on what you compare them to.
Talking in terms of my type of money. Because the capacity factor of those pump storage plants is very low, typically speaking. and so and they're extremely expensive to build.
Mm-hmm.
I also think that we're running out of possibilities, at least in the developed world.
Sure, there are definitely constraints on how much more you can build for pumped storage hydro. But you can look at the cost numbers, which is quoted here. You know, pumped storage hydro tends to be at the lower end of where battery technologies are right now. It may be a different story 5 or 10 years down the road. At least we can agree on that right now, almost all the energy storage capacity in the grid in the US as elsewhere is pumped storage hydro. And then you have a few small, you know, examples of batteries coming online, and there is a lot of interest in that, of course. So it's a growing market, but so far it's really pumped storage hydro which is the big technology. And this is where this center at Argonne comes into the picture. I'm not going to say much about that, but we have a big energy innovation hub which focuses on batteries, and they have some very aggressive goals of improving the lifetime and reducing the costs for battery technologies, moving beyond lithium-ion batteries. And that's one of their you know, slogans, that you need to go beyond the current lithium-ion batteries to reach the performance targets. So in this project that we are working on now, these are different types of applications for energy storage, going from at the bulk energy level, you know, energy arbitrage or supply capacity through ancillary services, which include, you know, different types of operating reserves and also other types of services. And then you have also potential contributions on the transmission side, on the distribution side, and also at the end user, which is more about reliability, you know, backup power, and potentially optimizing your energy use at the individual site level as a function of your tariffs. So we are mainly looking at least so far what's happening at the bulk power level and in terms of ancillary services in our analysis. Flexibility, of course, is important when it comes to renewables. And one important aspect of storage, if you compare that to a typical gas peaker of the same capacity, the gas peaker can only operate within a certain range, let's say between 10 and 50 megawatts here. So if you operate in the middle at 30, you can move up 20 or down 20. That's your, you know, how much reserves you can provide basically. For the battery, you can move in both directions. So you have a much wider flexibility range, which is valuable. Another thing is that the battery is always available. Whereas the gas peaker, the ability to provide spinning reserves or regulation is only there when you are committed and online. So that's important to keep in mind, that the battery can really provide services continuously. So this is an overview of the project, and we are looking at this, as I said, from a couple of different perspectives. We are working on resource characterization, how to generate scenarios for wind and power, you know, generation as a function of the weather. We are looking at how to represent storage in these types of power grid models, and we are doing stochastic commitment and dispatch, and also we do more like agent or profit maximization from the storage agent's point of view. So in terms of generating renewable scenarios, we are working with colleagues at Argonne who run numerical weather prediction models. So they can simulate the weather across a big or small domain. And like in this case, you use a model to generate a forecast. You compare that to observed weather variables. And based on that difference, you can estimate a stochastic process using something called Gaussian process modeling. And from that, you can move to scenarios for wind and solar power for the next day. So that's one piece of the puzzle here. But that's important how you to generate to characterize the resources in an adequate manner, and that's sometimes I think forgotten in the power world, that we don't pay attention to how this is done.
You need the Gaussian assumption.
Good question. That is a limitation here, but the advantage of using that approach is that you can you can model the uncertainty in multiple as a function of multiple variables. So it becomes you can handle much more dimensions with that assumption. We do have another approach which is called kernel. I mentioned that kernel density estimation, which is non-parametric. So for few explanatory variables, that's a better approach. But once you want to go into high dimensions, like multiple, spatial temporal correlations, it has its limitations because of the dimensionality challenge. So that's the advantage of the Gaussian process modeling. But we are looking at both approaches here. But the key is to capture both correlations in time as well as in space. And this example is focusing on the VEC area, where there are weather observations at these red and blue dots here that are used to calibrate the model. So, okay, so let's get to the commitment and dispatch decision. So in this case, we assume that energy storage is a system resource that is used to balance supply and demand in the grid. And we look at two stages, day ahead and what we call post-analysis stage, or more like real-time dispatch. At the day ahead stage, we do a stochastic unit commitment with wind power uncertainty. And then we simulate hour by hour the dispatch, more like in real time, using Monte Carlo simulations based on those.
Uncertainty in the system, the wind?
Yes, so far. In this example, it's only wind. And the stochastic unit commitment problem is so we try to minimize the expected production cost. It boils down to a mixed integer linear programming problem. We impose some reserve requirements, regulation, as well as you need to maintain contingency reserves, the largest single generator. And then instead of using a two-stage formulation, we split the forecasted wind scenarios, which is illustrated here, into multiple time segments for the next day. And for each time segments, we split that into what we call buckets. So instead of assuming that commitment decisions are the same across all the scenarios, which you do in two-stage stochastic unit commitment, we impose those constraints only for the individual buckets here.
Can you tell me what the reference is when you say it improved over what?
Yeah, it's actually another paper that is under review right now, but it's...
No, but I see that.
Yeah.
What is the reference that you're improving over?
So the first reference is a deterministic model. But then the more relevant benchmark here is a traditional two-stage model, where you don't have this time segments and bucket approach. So you just have the scenarios, and this builds more flexibility into your strategy. So that's what we compare here, and we do see significant cost savings.
Does everybody who works in unit commitment understand what's improvement over? Because
probably not, no.
Because I certainly don't know what the reference is.
Right. So, yeah, that's a good point. But there are lots of people working, at least on the research side of things, working on these types of formulations. So,
but if I don't know with respect to which one you're improving it, then I don't know how to judge.
Well, the reference is more from a stochastic programming, formulation perspective, a standard two-stage stochastic program where.
Because if John Birch is involved with this, then he's improving on his previous work.
Yeah,
Because he's been in this now for 25 years.
Sure, yeah. That is true. But the ideal solution, though, is to do stochastic dynamic programming, where you represent how the uncertainty unfolds for all time periods of the next day, for each individual hour. You have scenarios that branch out, but that becomes too computationally demanding to do. So this is kind of in between multi-stage and two-stage stochastic programming. But what I want to say is that also when it comes to real-time operations, we use the solutions from these individual buckets to guide the operation of the storage device in real-time operations. So that's...
Second question about your reserves policy.
Yeah.
Largest single generator contingency. Is that realistic when you have wind?
Well, that's kind of represents what you need to carry to deal with other types of uncertainty here. Then the stochastic programming formulation is supposed to take care of the wind power uncertainty. That's the assumption. Okay, so this is the case study where we generate a bunch of scenarios. We optimize for 20 wind scenarios in the day ahead stage using this approach I just described. We use one of the standard test systems, the reliability one. And we vary the amount of wind power from 15 to 25%. And we have one battery located at one of those wind farms here. And the constraints for the battery, it's shown here. It basically takes care of the energy balance. And also it makes sure that so the battery can provide energy as well as different types of operating reserves. So that's kind of captured in the set of equations here.
Wait, you said that the battery was a system resource.
Yes, that's the assumption.
Why would they have to place it at the wind farm?
Well, right, yeah, no, it wouldn't have to be placed there. That's just our assumption. We didn't look at optimal placement, actually. That may be elsewhere in the system. That's a good point. Okay, so here is the summary of day ahead results. And we can compare the upper part of the table is with energy storage. The lower part is without energy storage. And you can see that the system cost is reduced quite significantly. That's what's shown in the graph on the right here. So by introducing energy storage, you get around an 8 to 9% cost saving compared to the case without energy storage. So that's the total system cost, and this is just for one day that we are looking at so far. And you can break that down into more detailed results for like the amount of wind curtailment, which tends to go down, the amount of reserve violations, which has a penalty, actually is slightly higher with energy storage here. But the cost is substantially lower with energy storage in the system.
All you have is 3 values, right?
Sorry?
In this graph, all you have is 3 values.
Yes.
You have minor barometric sensitivity.
No. It's just
it's really 3 bars.
It's 3 points. Yes, yeah. That's right.
And is that the penetration of the wind?
Yes, correct. Sorry, yeah. That's the wind penetration from 15 to 25. And this is how the energy storage, the state of charge of the battery varies across those 20 scenarios. And it's the expected costs in the table above there. So, the next step would be to compare these cost savings, and then calculate what would be the required cost for the battery for this to break even as a potential solution. But we haven't done that yet. And that's the...
How big is the battery again compared to the amount of installed or the total capacity?
The battery is 50 megawatts. 50 megawatts. It's 3 hours, so it's 150 megawatt hours. And the peak load is, I think, close to 3,000 megawatts. And for the wind power, I don't know the max capacity, but the energy contribution is the percentage there.
Okay. Yeah. What kind of charge-up time do we have with that battery?
It is a 3-hour battery, so
it's symmetric.
Yes, that's right. That's the assumption. 90% efficiency, both directions. Yeah. So that's the cost savings at the day ahead stage.
Tell us a little bit about the reserve requirement. What does that?
Yeah, so the model has, from a systems perspective, it represents the need for spinning reserves, non-spinning reserves, and regulation. But they are not hard constraints, so there is a cost involved in the objective function if you violate those constraints. So that's why you get, relatively modest constraints, but there are more of them with energy storage. We were a little bit surprised at first when we saw that, but I think the model is a pure cost optimization. So probably the energy storage device makes it possible to commit less thermal units, and this is what comes out of the model. So those violations are represented in the total system cost numbers here. Okay, and then we also run this through the real-time simulation, and then we do this as a dispatch problem, but we only look 1 hour ahead, so it's limited foresight. We go from hour to hour, and we use a so-called persistent wind power forecast. The assumption is that the wind power will be the same in hour 2 as in hour 1, basically, and we simulate across 150 scenarios. And then the problem or the question is, how do you represent the energy storage use in real-time economic dispatch? Given that you only look 2 hours ahead in this case, that's the assumption. The renewables are still uncertain. Do you just pick a solution from the day ahead model, or do you impose some kind of bounds on where your energy storage device can operate? So we are exploring different ways of connecting the day ahead solution with the real-time dispatch. And the idea here is that based on what you find across scenarios in the day ahead model, you can impose bounds on how far up and down you charge and discharge your energy storage as you proceed through real-time operations. And we compare that approach here with, these are the same types of results again, the total system costs at different wind penetration levels. And the first one is if you impose a bound on the energy storage, if you use a fixed schedule from day ahead, and then if you use no schedule on an energy storage from day ahead, so you just let it operate freely based on a 2 hour ahead dispatch formulation, which you move forward sequentially. And what we find is that there is a significant saving in this case if you do impose that bound from the day ahead solution. You can look at numbers to the right here. Compared to the no schedule case, the savings are between 0.5% up to as much as 5%. But the numbers are a bit random and scattered though. So, but there seems to be a benefit.
How did the energy storage behave when you had the schedule?
Right. Yeah. Good question. It's so this is the result of the simulation for again for just 1 day, 25% wind penetration case. So the dark lines are the ones where there was a bound on how far up and down you could move, and that is compared to the lighter lines here, which are without any bounds or any schedule imposed on the energy storage. Then they branch out much more, as you can see. So kind of the bound keeps the energy storage within a certain range there, and you can notice that the bound forces it back to the the starting point at the end of the day there. So it does have an impact on how you end up dispatching in real time. Yes, that's a constraint. So that's one idea for how to connect day ahead solution with real-time dispatch. There may be other and better ways of doing it, but it's an interesting question how to transfer information from the day ahead solution into the real-time dispatch for an energy storage device, which doesn't have any intrinsic marginal cost associated to it. So
why isn't the state of charge at the beginning of the period known?
It is actually known here. So this is, I think, what's happening. You mean why it's all over the place in the first hour? Is that what you refer to? Or?
Yeah.
Yeah. So.
I mean, do they have? Are all those curves starting at the same point?
Yeah. Yes. In hour zero, they start at the same point, and then they move up and down. Yeah, that's right.
And they don't end up at the same point then?
They do end up at the same point if for the dark scenarios here, because that's a constraint. That's where we impose the bound. But if you don't impose any bound, they move all over the place. Okay, yes, so to summarize the results for storage and unit commitment economic dispatch, the day-ahead model shows significant cost savings from energy storage. And the second idea is that you may be able to improve real-time operations by using information from the day-ahead solution and impose bounds on how you operate the energy storage in real time here. But these are preliminary, and I should add the caveat that I showed results for one set of scenarios. We've been testing on different sets of scenarios, and the results, the cost savings are definitely dependent on the scenarios that you fit into the model, and also the savings from this bound approach in real time. So we are working on testing this across a wider set of scenarios. Okay, so I have another final topic here, but it's approaching 5 o'clock. Should I just give like the conclusions of this one maybe, or? Yeah. Okay, so just briefly here, the idea is to optimize energy storage based on prices. And basically what you want to do is to take advantage.
Now you're changing totally directions.
Yeah, well, it's still energy storage.
It's no longer a system resource.
That's right, yes. Okay. Exactly. It's still energy storage, but no longer system research. It's the idea. The objective is to maximize the profits from the day-ahead and real-time markets. So we assume that you can offer both into both of those markets. And to make a long story, so we optimize first for day-ahead only. Then we take the result from the day-ahead into a real-time model. And what we find is that and prices in day-ahead, the uncertainty is relatively small. That's the red lines here. The uncertainty in real-time prices, the blue dots, much wider uncertainty in real-time prices. And what we found in this one example here is that you can look at the profit. And these are different strategies. But the short story is that you can look at profit from the day-ahead market, profit from real-time market, and combined profits. And basically what our hypothesis is that if you own a battery, you basically are looking for price differences. You want to buy when prices are low and sell when prices are high. So by operating in both day-ahead and real-time markets, you have more opportunities to take advantage of such situations. So it's advantageous to bid both in day-ahead and real-time markets. On top of that, if you operate in both markets, you can also take advantage of potential energy arbitrage between the two markets. So
and are the discharging rates are correctly represented here in terms of the real time? Because you have only 5 minutes.
Well, yeah, no, it's very simplistic so far. So the real-time model here is actually doing optimization ahead of time. So you optimize for all the 24 hours.
And you use the first 5 minutes?
You optimize for all 24 hours. So it's still hourly time resolution. So when I say real time, it's not really 5-minute real time dispatch, but still the market settlements are done at hourly time resolution still though. So, but it's a rough approximation. But the conclusion I think stands that you want to take advantage of price arbitrage opportunities in both markets.
Is this for just energy, not also for ancillary service revenue?
Yes, good question. This is only energy arbitrage so far.
Are you guys looking at ancillary service revenue?
Hoping to get there. But the energy arbitrage, that's where the real big market is, you know.
I've heard the opposite, that most of the opportunities for making money with batteries is in
If they're fast responding. They have to be very fast responding because 2 to 4 seconds.
Oh, you're talking about here spinning with over.
But it's regulation. Regulation service.
Yeah, yes.
Fast responding, so it doesn't represent at all ancillary services.
No, this is an energy arbitrage. But the other thing is that okay, today the regulation market is very attractive. Because you are an early investor. But the size of the regulation market, like in PJM, I think it's 0.7% of the load. So it's a very small market, you know, in the long run. So
but if you make good profit, then it's okay. I can sleep well on that.
Yes, if you're an early, early mover in this market, but in the long run, I don't think, it's not gonna.
In the long run, we're all dead.
Yes, that's right.
I also saw that they were self-fulfilling. How much energy storage can the market tolerate before there's no price difference to harvest profit?
Yeah, good question. It depends on the load in the specific market. So, yes. Sure. Yes, I'll stop there. That's plenty of stuff, I guess.
Any questions? Thank you, Audun.
Sure.
Thank you.
Thank you. All right.
So
Nice to
I
meet
can't
you.
eat dinner. It's
Yeah.
my wife's birthday, so I need to.
Sure. That's understood. Yeah.
Can I get a copy of your presentation?